So far in this unit, we've talked about the different ways that you can define a wave. We talked about different properties, vocab terms like amplitude and wavelength. We also talked about how you can quantify a wave and use mathematical relationships to define those wavelengths and how it's related to the frequency and how it's related to the wave speed. Today, we're going to talk about what happens if more than one wave happens in the same place at the same time. Specifically, we're going to refer to this as wave interactions. Now, there is more of an umbrella term when we talk about how waves interact with each other, and we describe that as wave interference. So interference happens when more than one wave is in the same location at the same time. Now, something that's interesting with waves that is different than what we typically see with physical objects is typically if physical objects were coming toward each other, they would be able to occupy the same space at the same time. They would collide and they would stop. But waves actually pass through each other. So there will be a split second that they are actually together at the same time, producing a new wave, some wave that is some combination of the two waves that began. But after those waves pass by one another, after that split second that they're in the same spot, they will pass by and continue on unchanged. You have probably actually seen this in action if you ever looked at ripples in the water. The ripples will emanate outward kind of in that circular pattern. And if you have more than one source of a ripple, the circles are going to continue on past each other even when they collide. But there will always be this area where the ripples occur in the same spot, producing that interference. Now, there's more than one way that a wave can interfere. And we can describe these in two primary categories. The first, shown here on the left, is an interference pattern where you have two wave pulses that are both on the top of a wave. So if you imagine that you had like a long jump rope and you and your friend each created this pulse, sending it toward each other. As those pulses collide, they'll actually create a pulse in the center at the moment that they are in the same spot that is twice as big. Those two pulses will add together to produce what we call constructive interference. Now, this term makes sense. Constructive, like constructing a building, you're building it higher because both waves are contributing to one larger wave. If you had a wave pulse that was on the top, approaching a wave pulse that is on the bottom, they will actually cancel each other out. And for a split second, those waves will look like they're not there at all. Because the top wave cancels out the bottom wave, and we call this type of interference destructive interference. So constructive is when the two waves build a wave that is larger, and destructive is when they cancel each other out, either completely or to some extent. These two animations do a really nice job of showing what this looks like in terms of wave pulses in action. Now we can put some numbers to this, and this is the easiest math problem that you will see in this class. So for example, if we have a couple wave pulses here, this red wave pulse combining with this green wave pulse, you get an amplitude of 1 and an amplitude of 2. In the middle, they will combine to form a wave pulse with an amplitude of 3. The 1 and the 2 will add up to 3. Likewise, here in scenario B, 1 and 1 will combine to form 2. I would like you to predict what's going to happen in this scenario C. What will be the outcome, the final amplitude of that wave? Okay, you probably guessed it. It's simple math. 3 and 1 will make 4. The amplitude here for scenario C is 4. That is constructive interference. This wave pulse that is formed in the superposition of the waves is larger than either of the waves were to begin with. There's also a way to quantify destructive interference. Here, it's more like a subtraction problem or adding negatives. If you have a wave pulse that's a positive 2 in the amplitude on the top and a negative 1 on the bottom, they're going to combine to form an amplitude of positive 1, the 2 minus 1, basically. Here we have a positive 1 and a negative 3. So it's like 1 minus 3. You'll end up with an amplitude of 2, but on the bottom. So like 1 minus 3 is a negative 2. With that in mind, I'd like you to predict what should the amplitude be according to this scenario C, where you have 2 on the top and 3 on the bottom. All right, just like we saw for A and B, it's essentially like taking +2 minus 3 will give you a -1, which will show up as a wave with a -1 amplitude, or just an amplitude of 1 below that resting line. We can see this in real life as well. It's hard when we talk about this wave cancellation. How could that happen? And we don't really see waves like sound and light in these waveforms. But you have maybe experienced this. Some of you might actually have noise canceling headphones at home. There's a couple different types of noise canceling headphones. You could have noise canceling headphones that are just basically big shields that prevent you from being able to hear any sound that's coming in. Or you could have noise canceling headphones that are known as active noise canceling headphones. In active noise canceling headphones, it uses this idea of destructive interference to cancel out any sound that is coming from outside. There's actually a little microphone in the side of a noise canceling headphone. It picks up the sound from your environment, runs it through some transformation through some electronics, and then actually emits more sound through the headphones than just your music or whatever you're trying to listen to in the headphones. And that extra sound that's emitted is actually the opposite of the sound that is outside in your environment. So whether that's just kind of the drone of an airplane, if you're on an airplane, or just kind of background noise on a subway, that cancellation produces a sound that you can't hear. I'm going to try to get this so this animation is working again. Sound waves are longitudinal waves, which is kind of this pressure sort of wave. As you can see here, if you combine these two waves, wave A being the sound that is outside, and wave B being this extra sound signal, you can see that they actually perfectly cancel each other out. And instead of having these pressure waves, you end up with this perfectly neutral pressure, which would result in you not being able to hear any sound at all. If that wave pulse bounces off the side and comes back, you end up getting all of these reflections going on. So say you were trying to send a pulse down a jump rope to a friend, and it would send all the way down. It would actually bounce off their hand and come back. And if you kept sending pulses, and they kept bouncing back, you're going to have interference all the time going on in that jump rope. If you hit just the right frequency, you're going to produce what's known as a standing wave. This is a really nice animation of what a standing wave might look like. It kind of looks like a jump rope in a certain amount, a certain way that you have these areas that are really, really moving. You also have these areas that aren't moving at all. Now, it's pretty easy to see this in an animation, but it's hard to draw that when it's not animated. So typically the way we are going to draw this example of a standing wave, if we can't have it animated, is we're going to draw it like this. This doesn't mean that both of these ropes are occurring at exactly the same time. It means that the wave is oscillating between this red position and this green position. Here I have it color-coded. You don't have to have it color-coded to show this, but this is how we're going to draw a standing wave. This wave that is finding this resonant frequency and bouncing back and forth in this repeating pattern. Now there's some properties that we can define with the standing wave. First of all, these points here in this animation can be drawn in here as well. These are the points that have no amplitude at all. If you were to come up and grab this rope at any of these dots, you wouldn't change the pattern at all because it's just bending back and forth between there. It's not actually moving up and down. This has a special name. We call these nodes. The nodes are the part of the standing wave that have no amplitude. You also have these areas of really, really high amplitude. It's where it's vibrating the most. This is the opposite of a node. We call this an antinode or antinode. That's where the vibration is the largest. So nodes and antinodes are kind of our two main properties in a standing wave. And we can look at some standing waves and define them numerically in a variety of different ways. The first, actually the easiest one to do, is to count the number of standing waves. The number of standing waves, if you were to imagine that this were like a jump rope. The number of standing waves is how many jump ropers could jump rope in that spot. So here, in this first example, this is the simplest standing wave that we can have with one node on either side. So 2 nodes and an antinode will give you 1 standing wave. So if you imagine a little jump roper jumping in there, that is 1 standing wave that's there. This next one has 2 antinodes, or 2 bubbles. We'll call that 2 standing waves. Next one is 3 standing waves. How many standing waves would then be in this last drawing here? If you follow the pattern, it's pretty clear that this last one is going to be 4 standing waves, a standing wave representing each antinode in that system. Okay, if we look at the number of wavelengths, this is a slightly different question. And this is honestly one of the hardest parts of this topic, is talking about number of wavelengths, we need to remember that this picture isn't actually all happening at once. If you were to take a picture of someone producing a standing wave, you would actually only see one of these colors at a time. So you'd see only the blue part or only the red part. It's oscillating back and forth between these positions. So let's say we were just looking at the red. How many wavelengths is that red line? We start at the middle, we go down, we go up, and we end up back where we started. So in this particular example right here, that is only 1 wavelength. That means that here, the one above it, is only half of that first one, so that is half a wavelength. This third one is 1.5 wavelengths. You might notice a pattern here. The number of wavelengths is always half the number of standing waves. So with that in mind, how many wavelengths then are in this last picture? If the number of wavelengths is always half of the number of standing waves, 4 standing waves mean 2 wavelengths. Or you can look at the red part here, goes up and down and back, that's 1, up and down and back, that is 2. All right, the last piece here is if you are given information about the length of this rope from end to end, you can actually figure out how long 1 wavelength would have to be. The easiest one to look at here is this second one. We already said that there is 1 wavelength from end to end, so that is 1 complete wave. If I give you this information that from end to end, that is 12 meters, 1 wave in 12 meters means that the wavelength is 12 meters. 1 wave in that amount of space. If half of a wave happens in 12 meters, if you think to yourself, okay, half a wave in 12 meters, if I needed a whole wave, I would need 2 halves. So 12 plus 12 will give me a wavelength of 24. It gets a little bit harder if you go down. Here, we said that this part here, these 2 standing waves, that is 1 wavelength. And then we have another half of a wavelength. So from end to end, that's 12. 1 wavelength isn't quite 12. It's 2/3 of that. 2/3 of 12 is going to be 8 meters. Another way to think of it is if you were to divide 12 into 3 standing waves, each one gets 4 meters, and it takes 2 standing waves to make 1 full wavelength. All right, this last one, I would like you to predict what is the measurement, how many meters is 1 wavelength here? If end to end, this is 12 meters, and overall, that has 2 wavelengths. All right, if you can fit 2 wavelengths in 12 meters, that means each wave is exactly 6 meters. Now, it's easy to think of a standing wave as like a jump rope, but the reality is most of the waves that we're talking about in this particular unit aren't physical waves like that. It's waves like sound and light, something that you can't see the wavelength quite as easily. So there are some nifty ways that you can visualize sound. One is using a Rubens tube. If you pump a big tube filled with methane gas and poke a bunch of holes in the top, it's like you've created a bunch of little Bunsen burners. And the flame actually rises higher if it's an area of high pressure. An antinode is essentially an area of high pressure in a longitudinal wave. You may remember that as a compression. And a node is a rarefaction, an area of low pressure. And you can see this wave form in the fire, which is a really, really cool way to see a standing wave.